Hi, everybody. Welcome back. So in this video, we'll be looking at a special test. I'll say a test to show that if a function is analytic. And this is called using the Cauchy-Riemann equations. So let's get started. Now, in the last video, we looked at the definition of the derivative. So let me write this out. F prime of z is equal to the limit as delta z goes to 0 of f of z plus delta z minus f of z divided by delta z. This is the definition of the limit, okay? So for the purposes of this video, we're gonna assume, let me start off by saying this. Let us assume f prime of z exists. Okay, so a derivative exists, all right? And then we're going to come up with some way to show that a function is, well, differentiable. Okay, I'll say that. So also a complex function, right? Suppose, so a complex function, you can decompose a complex function in terms of the real and imaginary components. So if we suppose that f of z is equal to the real component, which is a function of x and y, plus the imaginary component, which is also another function of x and y. Okay, so let's suppose we have that. And delta z, this is equal to delta x plus I times delta y, right? Okay, so we can also, so by using these definitions, we can decompose the limit into components. We can decompose the limit in terms of the real and imaginary components. Now, before I move on, I need to remark a couple of things. So this will be content that you've seen in Calculus 3, possibly. And this refers to what are called the partial derivatives, okay? Partial derivatives. And they are labeled as this. These are not twos, these are just curly D's, all right? So you'll see curly symbols like this, right? Or you may see something like this, okay? But regardless, I'll explain what these are. So the only thing you need to concentrate on are these two symbols here. So what this means is you're going to take the partial derivative with respect to, WRT means with respect to x. And this right here, this is the partial derivative of with respect to y, okay, with respect to y. So, so in terms of in terms of a limit, uh, for a function, so for a real, function in the form, not z, oh God, u equals to f of x y, let's say. All right, so I'm saying here is that that f is a real function with two variables, x and y. Okay, so the definition of this quantity, the partial of f with respect to x, this is how you would read this. So the partial of f with respect to x. Okay, this equals to this limit here. It equals to the limit as x, y approaches to, or I should say, as delta x goes to 0 of f of u, I'm sorry, shoot. I have to be careful here. X plus delta x y minus f of x y over delta x. Okay. So this is how you would express the partial of f with respect to x in terms of a limit. Okay. And the partial of f with respect to y, this is equal to the following definition. The limit as delta y goes to 0 of f of x and y plus delta y minus f of x y divided by delta y. Okay. So this right here is the partial of f with respect to y. Partial of f with respect to y. Okay. So if you have not seen this in Calc 3, don't worry. Okay. What this means is you are going to differentiate the function in terms of that variable, and then you're going to leave all of the other variables constants. Okay, so I'll show you an example on how we would do that. But for now, just you can just take my word for it, okay? But this is what the partial derivatives mean in terms of multivariable functions, right? Partial of f with respect to x is equal to this limit. The partial of f with respect to y is equal to this limit by definition. Okay. So with that, we should be able to derive the Cauchy-Riemann equations. Okay. So we have this limit, z plus delta z minus f of z divided by delta z. You don't have to write this down, but so this is equal to the limit as, let's say, delta z goes to 0. So we can write out f in terms of the real and imaginary components. So z is equal to x plus iy, and then delta z was delta x plus I times delta y, right? So we'll have u of x plus delta x, and then y plus delta y, plus I times v of x plus delta x, and then y plus delta y, minus u of x y plus I times v of x y divided by delta x plus I times delta y. Okay, so this would be the limit, okay, of this quantity here, reduced down into the real and imaginary components. Okay, so if you look at the different partials, well, it should equal to the same limit. So in other words, if we look at the different limits across these two paths, they should equal to the same number if we're assuming that a derivative exists for f. So that is exactly what we're going to do. Okay. So the first path, what we're going to do, that we're going to take is we're going to go along delta y equals 0 and delta z equals to delta x, right? So this limit right here, this will reduce down to saying this quantity, right? So this would equal to the limit as delta z goes to 0 of, so delta y is 0. So u of x plus delta x minus, oh shoot, x plus delta x, I have to be careful, and then y minus u of x y over, so delta y is 0, so this is delta x. And then I'll have a plus I times the v function. V of x plus delta x, and then y minus v of x y divided by delta x. Okay, so hopefully that made sense. So keep in mind, this has to equal to f prime of z, right? F prime of z. So, okay, the first term, this limit, well, this would equal to the partial of u with respect to x, right? That's the definition of this partial here, right? We're only varying x and we're fixing the y coordinates. So this is the partial of u with respect to x. And this limit right here, this is the partial of v with respect to x, okay? So therefore, this quantity would equal to the partial of u with respect to x plus I times the partial of v with respect to x. Okay, so this is the first time. This is the first path. The second path would be this path right here. If we go along, so if we go along delta x equals 0 and delta z equals delta y, right? Okay. Keep in mind, this also has to equal to f prime of z, right? So limit as delta z goes to 0. So what that will reduce down to is, so the u's would be u of x, y plus delta y minus u of x y over I times delta y, okay? Plus, oh shoot, plus, oh geez, plus I times v of x y plus delta y minus v of x y divided by I times delta y. Okay, so what this will equal to is, okay, so the second component, the i's will cancel, and this quantity right here, this would be the partial of v with respect to y. That actually is the real component. This component over here, this is the imaginary component. Okay, the imaginary component. So this would equal to, if I do complex division, so this is minus I times u of x and then y plus delta y minus u of xy divided by delta y. We'll get this, okay? All right, and so this would equal to minus I times the partial of u with respect to y plus the partial of v with respect to y, okay? And this will also equal to f prime of z, okay? F prime of z. Since both of these quantities here and then here have to equal, then so are their components. They would have to equal. And that is where we will derive the Cauchy-Riemann equations. So Cauchy-Riemann equations, named after Augustin Louis Cauchy and Bernard Riemann. Okay, so the first set of equations is if the real parts are equal. So we will have the partial of u with respect to x is equal to the partial of v with respect to y. Okay, the partial of v with respect to y. So these would be the real components that are indicated here and here. And the imaginary components would also have to equal, right? So the second type of equations is the partial of u with respect to y is equal to minus the partial of v with respect to x. This, folks, is the set of the Cauchy-Riemann equations. Got one more word. Equations. Okay. And these equations will be useful to show if a function is analytic on a given domain. All right. Or on an appropriate domain. Okay. So let's look at an example, shall we? So here's an example. Show that f of z in terms of the real and imaginary components is equal to e to the minus x cosine of y minus I times e to the minus x sine y is analytic on a given domain. All right. Okay. So pause the video and I want you to work on this on your own, okay? And try to figure out which domain would be suitable for this function, right? Okay, welcome back. So I assumed you worked on this example. And let's see the test for analyticity for this function, right? So what we want to do is look at the real and imaginary components. So this is the real component and this is the imaginary component and the negative there too. So the real component, u of xy, is equal to e to the minus x cosine y. The imaginary component, v of xy, is equal to minus e to the minus x sine y. Okay. So let's actually compute the partial derivatives of u and then v, right? So partial of u with respect to y. Partial of v with respect to x. Partial of v with respect to y. Okay, let's start off with the partial of u with respect to x. All we do here is we differentiate the functions that contain x, and all the other variables we leave out as constants. So, for example, partial of u with respect to x, we differentiate e to the minus x, and we treat cosine of y as a constant. All right. So in this case, this would be e minus e to the minus x cosine y. Cosine of y is a constant. Partial of u with respect to y, this time we differentiate the functions that contain y, the variable y, and we leave out the other variables as constants. Okay. So So we'll leave out e to the minus x as a constant. And then the derivative cosine of y is minus sine of y. So minus sine y here. So I'm going to reduce this down to minus e to the minus x sine y, right? Okay. Same thing for v. Partial of v with respect to x, this would be e to the minus x sine y. E to the minus x sine y. Partial of v with respect to y, this is equal to minus e to the minus x cosine y. Okay, that's how you compute those partial derivatives. Okay, do we have that the partial of u with respect to x is equal to the partial of v with respect to y? Yes. Yes, that is true. Partial of u with respect to x is equal to the partial of v with respect to y. Okay, check. Second test. Do we have the partial of u with respect to y equals to minus the partial of v with respect to x? Yes, we do. We have the other test. Notice here, partial of v with respect to x is this quantity, but that is equal to minus e to the minus x sine y, which is the partial of v with respect to y. So we also have the other relationship. The partial of v with respect to y is equal to minus the partial of v with respect to x. So therefore, they satisfy the Cauchy-Riemann equations. And if you notice, we can rewrite these quantities as cosine y over e to the x. And the imaginary component, we can write this out as sine y over e to the x. Okay, e to the x is never zero. So we can say that f of z is analytic on all of the complex numbers, right? E to the x is never zero, right? E to the x is never zero. Okay, so this function will be defined for all values x and y. So therefore, it's defined in all of the complex plane, C. Okay, so this here is an example of an entire function. It's an entire function. Pretty cool, right? I think so. So we have some further requirements to show analyticity for a function. So let me write out the criterion for analyticity of a function f of z. Okay, so suppose u of xy and v of xy are continuous. And have continuous first order partial derivatives. So in other words, the partial of f with respect to x, partial of f with respect to y, partial of g with respect to x, and the partial of g with respect to y exists. Okay, that's what that means. In a domain D. Okay. If the functions u and v satisfy the Cauchy-Riemann equations at all points in the domain D, then and f of z equals f U of xy plus I v of xy is analytic on D. Okay, on D. All right, so that is the criterion, excuse me. Okay, so if we have a multivariable function, u of xy and then v of xy, and if they have first order partial derivatives exists in a domain D, and if they satisfy the Cauchy-Riemann equations, then your function is analytic on that specific domain D. Okay. So, for example, okay, so for example, is an appropriate domain D. Okay, so what you want to do is see if this function f satisfies the Cauchy-Riemann equations, and then from there, um, you want to gather where on the complex plane is our function analytic. Okay, since we're dealing with rational functions for our real and imaginary components, the best idea is to look at where the denominator would cause to be zero, right? Look at values for x and or y would cause division by zero. All right, so I'll give you a few minutes to work on this example. Pause the video and try to look and think about this for a bit. Okay, so I assumed you worked on this example. Let's see if f satisfies the Cauchy-Riemann equations. So if u of xy is equal to the real component, x minus 1 divided by x minus 1 squared plus y squared, v, the imaginary component, this is equal to minus y over x minus 1 squared plus y squared. Okay. What we want to do is look at the partial derivatives, right? Partial of u with respect to x, and then the partial of u with respect to y, and partial of v with respect to x, and the partial of v with respect to y. Okay, so here we go. All these are going to use the quotient rule. Okay, so we'll have low times d high, partial u with respect to x, and that's 1 minus x minus 1 high times the derivative of the low function, which is just 2 times x minus 1 divided by the low function squared. So x minus 1 squared plus y squared, all that squared. Wow. Okay, so partial of u with respect to y, this one's a little bit easier because the x's are constants. So you'll have x plus 1 squared plus y squared times the derivative of the low function, which is 0, times the derivative of the numerator, which is 0, minus the high function, x minus 1, times the derivative of the denominator. So this is 2y over x minus 1 squared plus y squared squared. Okay. All right. How about the v function? V function. All right. So partial of v with respect to x. That is the low function times the derivative of the high function. So that's 0 minus high. So minus negative y, so that's a plus. I'll just do plus. Plus y times the derivative of the low function, which is 2 times x minus 1 divided by the denominator quantity squared, which is this. Okay. X minus 1 squared plus y squared squared. Saying square a lot. All right. Partial of v with respect to y. So we'll have x minus 1 squared plus y squared times minus 1 minus high, so plus y times the low. So that is 2y over the denominator squared, x minus 1 squared plus y squared squared. Since the denominators are all the same, all you got to do is just look at the numerator numbers for each of the partials. Okay, so the partial of u with respect to x, so that is x minus 1 squared plus y squared minus 2 times x minus 1 squared. So the numerator here, so that would be y squared minus x minus 1 squared. Okay. And we have that here in the partial of v with respect to y. So this quantity, this is equal to 2y squared minus y squared. So we'll have a y squared minus x minus 1 squared. So we can conclude that the partial of v with respect to x is equal to the partial of v with respect to y. So we have that checked. Partial of v with respect to y. Okay, now on to the next set of partials. So the partial of v with respect to y, well, that is, so this is just 0. So we'll have the numerator being reduced down to minus 2y times x minus 1. Also, with this numerator here, right, so this will be 2y times x minus 1. So therefore, this quantity, the partial of v with respect to y, this is equal to minus the partial of v with respect to x. Okay. So we also have the other set of Cauchy-Riemann equations satisfied. Okay. So we have our function being differentiable. Now, the second part of this question is, where is our function analytic? So we have to go back to f of z. In the denominator, we have what looks like to be an equation of a circle. Okay. The equation of a circle, right? X minus 1 squared plus y squared. This cannot equal to 0. So therefore, we should have that y squared should not equal to, well, really, I should write it out like this. So really, x minus 1 squared cannot equal to minus y squared, right? And if I square root both sides, I'll have x minus 1 equals to plus or minus the square root of minus y minus 1 times y. So in this case, it will be plus or minus y, I times y. Okay, I times y. So x is equal to 1 plus iy, or x is equal to 1 minus iy. Okay, so So 1 minus IY, or just, yeah, right. So x minus IY equals 1, or x plus IY is 1. Okay. So really, it's just yeah, so it's that x equals 1, right? X equals 1 or y equals 0. X equals 1 and y equals 0. Okay. That will cause division by 0. Okay. So it's analytic at everywhere else except the point at 1, 0. Okay. So hopefully that made sense. Um, so so it's analytic at the point 1, 0. Okay. So hopefully that made sense. Um, okay. So another example could be something like this. So here's another example. Square minus x. Okay, so I want you to think about this example. Now, this time we're going to look at which set in the complex plane would make this function analytic. Okay, so pause the video and I want you to work on this for a bit. All right, so I assumed you thought about this for a couple minutes. So uh, really, we're going to look at the real components, the real component 2x squared plus y, and then the imaginary component, v, y squared minus x. So if you notice, if you look at the partials, partial v with respect to x and the partial v with respect to y, and the v partials, partial v with respect to y. Oh, shoot. Okay, partial v with respect to x, this is 4x. Partial v with respect to y is 1. Partial v with respect to x is -1. Okay. And then the partial of v with respect to y, that's 2y. Okay. So as you notice, these sets of equations are true, right? The partial of v with respect to y is equal to minus the partial of v with respect to x. So that's good to go. What's going to have problems is these different sets of equations, right? So 4x does not clearly equal to 2y if x does not if they don't equal to each other. So what we're going to have to do is find conditions on x and y where the partial of u with respect to x is equal to the partial of v with respect to y. So in this case, 4x equals 2y. So this will constitute a line. So y equals 2x in the complex plane. So this is the So this is where the function is analytic, y equals 2x. Y equals 2x. All right, so that will be the step on where that function is analytic. Okay, so the last portion I want to talk about is I don't want to give away any spoilers because for this problem because you're going to work this on your own. There are Cauchy-Riemann equations in polar coordinates. And I left this as an exercise. But I'll give you some before I do that, actually, yeah, I'll just go over it. So I'll go over this the equations in polar form, and there's one more fact I have to go over. And then I'll leave you to do your homework. Homework. So if we assume that f of z is equal to this function, right, into its real and imaginary components, and u and v satisfy the Cauchy-Riemann equations that were stated previously. What you want to do is set x is equal to r times cosine theta, right? That's how you figure out the x coordinate. The y coordinate is r times sine theta. So x is a function of r and theta. And then y is also a function of r and theta. So this will involve using the chain rule in multivariable functions. The chain rule in multivariable functions. So here's how it goes. So we have two functions, u and v. So u and v are a function of x and y. So you want to draw in branches like this. So u and v are functions of x and then y, like this. But x and y are is a function of r and theta. Okay. So to get from these lines, so this would be labeled as the partial view with respect to x. This is the partial view with respect to y here. And these lines on the bottom, these will indicate the partial of x with respect to r, partial of x with respect to theta, partial of y with respect to r, and the partial of y with respect to theta. And then likewise, these lines will be for partial of v with respect to x, partial of v with respect to y, partial of x with respect to r, partial of x with respect to theta, partial of y with respect to r, and the partial of y with respect to theta. Okay, so what we want to do is we want to establish a set of equations for the different partials, the partial of u with respect to r, the partial of u with respect to theta. And then we want to figure out the partial of v, excuse me, partial of v with respect to r, and the partial of v with respect to theta. Okay. Taking note that x and y are equal to r cosine theta and r sine theta, respectively, right? So first, in order to figure out the partial of u with respect to r, well, one way is we can take the partial of u with respect to x, and then we can take the partial of x with respect to r. So one way is taking the partial of u with respect to x times the partial of x with respect to r. And then another way is we can take the partial of u with respect to y, and then taking the partial of y with respect to r. So this is plus the partial of u with respect to y times the partial of y with respect to r. Okay, that's how you figure out the partial of u with respect to r. Likewise for theta, we just do the same thing, right? Take the partial of u with respect to x, partial of u with respect to x, and then times the partial of x with respect to theta, plus partial of u with respect to y, times the partial of y with respect to theta, right? So over here. Okay, partial of y with respect to theta. Okay, we do the same process with the partial of v. Partial of v with respect to r. Well, it would be the partial of v with respect to x times the partial of x with respect to r, right? So going down through this branch of the tree. And then plus the other way is, well, take the partial of v with respect to y times the partial of y with respect to r, right? Times the partial of y with respect to r. And then likewise for theta. Likewise for theta. We'll do this color, I guess. Yeah, so take partial of v with respect to x times the partial of x with respect to theta, and then plus the partial of v with respect to y and the partial of y with respect to theta. That should be enough for now. Okay, and then just assume that the Cauchy-Riemann equations are satisfied for u and v, and then you'll derive the Cauchy-Riemann equations in terms of polar coordinates. All right, so there's one more thing I need to mention in this section, and they refer to when complex functions are constant. So let's look at constant functions. So suppose f of z if that's y is analytic on a domain B. If the modulus of f of z is constant on capital B, then so is f of z. So if the modulus of f of z is the same on all points in your domain D, then you can say that f of z is constant. The second part is if f prime of z is equal to 0 in D, then f of z is equal to c for some constant c. So this is in D here. Okay. So those are what are referred to as constant functions. And there's going to be a very powerful theorem which involves entire functions and them being a constant, right? So yeah, it's called Louisville's theorem. Louisville's theorem. And we'll go over this in much detail, much more detail. I believe an entire function is constant, I think. I don't know how it goes, but it's somewhere in that nomenclature. So, but for now, this is the section on Cauchy-Riemann equations. So if you have questions about the content in this in this video, please let me know. And here's some problems for you to check yourself for comprehension. So page 157 through 158. 4, 6, 10, 12, 14, 15, 18, 20, 25, and 33. Yeah, so if you have questions, let me know. I hope you enjoyed this video. Thank you for watching. In the next video, we'll look at harmonic functions. So stay tuned. See you soon.